Hello everyone, my name is Aadarsh Sahoo. I'm a fourth year undergraduate student from the Department of Computer Science and Engineering, IIT Kharagpur, India. I'm going to present our work, Mitigating Dataset Imbalance via Joint Generation and Classification. This is a joint work with Ankit Singh from IIT Madras, Rameswar Panda and Rogerio Feris from the MIT IBM Watson AI Lab, and Abir from IIT Kharagpur. Deep learning is enjoying enormous success in solving computer vision tasks. But these models are vulnerable to imbalanced data, which makes the learning unreliable and biased. Imbalance in data cannot be avoided and is encountered while solving almost every real-life problem, from medical image analysis to self-driving cars. The figure illustrates how from the left to the right, the decision boundary shifts as the imbalance in the data increases and the classifier tends to classify almost everything as the majority class samples. Coming to the prior approaches in solving imbalance, sampling-based methods modify the imbalanced data in order to provide a balanced distribution to train the classifier. Undersampling randomly samples a subset of the majority class having the same cardinality as that of the minority class, resulting in a balanced distribution. Oversampling in the other way around repeats the samples in the minority class until both the classes have the same number of data points. Algorithm-based methods try to modify the cost function for training the classifier. The cost-sensitive approach penalizes the misclassification of a minority class example more as compared to that of the majority class examples, depending on the degree of imbalance present in the data. Thresholding applies a similar concept, but at the stage of inference, by multiplying the predicted probabilities according to the prior probability of occurrences of these classes in the training set. Recent methods like class balanced loss propose a loss depending on the effective number of training examples per class based on the fact that the additional benefit diminishes with increasing number of samples. Synthetic minority oversampling technique, or SMOTE in short, uses convex combination of minority class examples which creates additional examples in between the existing samples to augment the training of the minority class, which is illustrated in the figure shown. Now in our proposed framework, we utilize CycleGAN, which consists of two generators. Let us consider a case of classifying the images of horses and zebras, where horses are in majority. So we take an image of zebra and translate it to its corresponding horse image. The key to the success of CycleGAN is the cycle consistency loss, which is incorporated when the generated horse is forwarded through the other generator and the reconstructed zebra image along with the original zebra image contribute to the cycle consistency loss. Similarly, we translate the horse images to that of the zebra and end up with an augmented set of images to train the classifier further. With all the losses involved, we can train the system involving both the CycleGAN as well as the classifier. We propose two modes of training. The first one being augmented mode, in which we pre-train the CycleGAN separately without the involvement of the classifier and use it as an augmenter while training the classifier with the weights of the CycleGAN frozen. The second one is the alternate mode. Here we train the CycleGAN system and the classifier system turn by turn in an alternate fashion, encouraging both the systems to learn from each other. For a given phase, the classifier is trained with the weights of the CycleGAN frozen, and in the next phase, the CycleGAN is trained keeping the weights of the classifier frozen. But the classification loss from the classifier is backpropagated to the CycleGAN, making the classifier an additional teacher for the CycleGAN. And this procedure is continued until the end of the training. We particularly adopt this framework to additionally improve the performance of the CycleGAN towards imbalance and to make the adversarial training process stable. Now, CycleGAN translates images as opposed to generating them from random noise. The conversion of images involves the transformation of the content or the objects of interest present in the image while keeping the context or the semantic surroundings unchanged. This helps the classifier to focus and learn the features from the content instead of overfitting to the context, which is essential in mitigating imbalance and making the classifier robust. Here are the details of the loss functions used to train the system. We use a weighted binary cross entropy loss to train the classifier, where gamma represents the imbalance ratio of the data, while an adversarial loss and cycle consistency loss for both the classes to train the cycle gain along with an identity loss. A balanced binary cross entropy loss from the classifier is used to train the cycle gain in the alternate mode of training for stability. We provide results by performing experiments on 3 publicly available datasets. CelebA is a face dataset containing images of over 10,000 celebrities. We analyze imbalance based on 2 genders, male and female, with the female as the majority class. CUB 200 contains images of 200 different classes of different bird species, which is used for fine-grained classification. We choose to classify between 2 similar-looking species of sparrow and flycatcher, with sparrow as the majority class. Similarly, horse to zebra contains images of horses and zebras, which, unlike the birds, are distinctive. We take the horse as the majority class, while the zebra being minority. The number of images in the majority class is fixed, and the size of the minority class is varied to generate different degrees of imbalance. The exact number of images is chosen depending on the availability of images for each dataset. For evaluation, we use F1 score for the classifier, as it balances the precision and recall to provide a metric appropriate for data having skewness. For cycle gain, as we are experimenting in the low data and high imbalance regime, instead of inception score, which requires ample of data, we fine-tune an inception V3 model on a balanced training set and find the accuracy of it in classifying the generated samples, and we call it inception accuracy instead. Here are the F1 score values for the minority class of CelebA and the CUB dataset. Our proposed method clearly outperforms the prior approaches in the majority of the cases and is more promising when the imbalance is high. For example, in the highest imbalance scenario for the CelebA dataset, our method increases the F1 score by more than 5 folds with respect to the vanilla model. Similar trends are observed through all the 3 datasets. This table shows the inception accuracies for the vanilla cycle gain and the cycle gain obtained after the end of the alternate mode of training. It is clear that alternate mode of training helps the cycle gain learn better representations by additional knowledge which is provided by the classifier. The corresponding results for horse to zebra dataset can be found in our paper. Qualitatively, it can be seen that the alternate mode cycle gain produces better translated images with less noise and more relevant perturbations as compared to the vanilla cycle gain. Here are some generated samples from the 3 datasets corresponding to the highest imbalance ratio for both the minority as well as the majority class. In terms of explanation, both of our methods give proper explanations for the classification decision made. We use RISE and GradCamp for generating the heat maps for comparison. In both of the cases, it can be observed that the vanilla model overfits to the surroundings of the image and misclassifies, while the proposed method focuses on the object to take the decision as we designed the framework. With this, I would like to conclude. Thank you.